Okay, Trapper Keeper. Today's class is not a trap. DSA is the best. Super stoked. You're going to love DSA as much as I love DSA by the end of this. And if not, you're either in or you're out. No, just Heidi Klum. I don't do a good Heidi Klum. I do a better, the guy I really like on the show, which I don't remember right now. Tim Gunn. Nobody's like, no, you don't. That impression is crap. Oh my God, Nilbert. But that's okay. Okay, so we'll eventually hit some new DSA stuff. Today we're just going to do a little bit of review DSA stuff, see how long this goes. We'll either split this into 2 lectures or pop it all out in the morning. First concept we're going to be reviewing is the big O. Everybody wants that big O, you know? And this is big O. So that's going to be great. Big O is all about time complexity, space complexity. How do we feel about big O? Can you give me a thumbs up, thumbs down, or a in the middle hand? How about in the non-verbal feedback feature? Because not everybody's got their camera. So that way I can kind of like get an idea where
what
we're
would you say is like in the middle?
Sorry, Fowler?
What would be in the middle?
Oh, the hands clapping.
And only about the stuff that we've learned, right? So like we didn't learn some of the big O stuff.
Well, it's just the idea of identifying time complexities and knowing the different ones. The bottom one just keeps flipping between 3s and 4. Yeah, there we go. I don't know who's doing that. Okay, so overall we're in the middle. A couple thumbs up people lost their confidence and put it in the middle after they saw the rest of the class. Okay, let's start talking about it. I'm gonna share my screen while we talk. And start just doing this. So I've created a new folder here called DSA. This is in our 6.4 lecture notes, and I'm going to have a different file for each one of our concepts that we end up talking about. So for this first one, we've got big O. So let's talk about the different time complexities. So in the chat, get ready to type to me the fastest time complexity. Okay, on the count of 5, I want you to make the fastest one. So that's 5, 4, 3, 2, 1. Let's see it. All right.
Were we supposed to type it in notation or?
Either. It doesn't. Either one's fine. Okay, so Marvin, nice, thank you. David just wrote O. Danny, and interesting. Jay says constant. Karen, constant. Samantha, constant. Nilbert, constant. Deja, constant. Brutus, constant. Giovanni, Shia, and Square. And Square is not quite going to be the fastest there. We see O of 1s. And wait, okay. What was the question? Sin, sorry if you're getting cereal. That's on you. Okay. So the fastest one here is we're going to big O, we'll say fastest to slowest. And so the fastest one is, in fact, our O of 1. Whoops. O of 1, which is constant. Can somebody give me an example of what a constant thing is?
Retrieving a single item from an array.
Absolutely, yeah. So we'll say keying into an array. I'm going to say object because arrays are a type of object. But array, object. What's another constant thing?
Printing a string.
Okay. Sure, I'll say a constant log. Okay, what else is constant?
Not sure if objects like follow that rule, but I'm keying into a specific key in like one object or something like that.
Yeah, definitely. We've already.
Oh,
check your
okay, cool.
screen, that's
Sorry,
written down.
I just woke
Yeah.
up. Very sorry.
That's okay. Okay, so also math operations. Okay, so a number plus a number, that's a constant. Okay. What is the next fastest one? Okay, so we're gonna write this in the chat. In 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Show me the money. Okay, so we get a lot of linears here. Brutus, Eon, David, Karen, Henry, Nilbert, Deja, Javon, Ujwagabasi, Kong, Shia, Sin. So everybody says linear. That is not correct. Linear is going to go here. Let's talk about linear for a second. So O of n, which means linear. And linear is, we can think of iterating through an input of, we can say, unknown length. Okay, that's what I would think of that. So if we're having a function that takes in an array and we're got to go all the way through it, or some string, but we don't know ahead of time, like if the array is always going to be the length of 5, always, that fits like into the constant, because we know it's going to take 5 iterations no matter what every single time. But if we don't know the length of the array, maybe the length of the array is 5, maybe it's 10, maybe it's 1,000, right? For each time n gets incremented by 1, we have to do one more iteration. So because of that, as n grows, the amount of steps we have to do grows linearly in comparison to n. So that is why iterating through an array, through a string where we don't have a defined length ahead of time, is going to be linear. Okay, so Fowler has updated his answer now, it looks like, to the other one. Great. And so, any questions on linear before we jump in, though? Okay, so the actual answer here that I'm looking for is there's a nice little number, one in here between, which is O of log n, which is also considered logarithmic. Interesting. So logarithmic, what's that look like? So yeah, let's stop this share so I can get close to you all. So logarithmic is this idea of, as we're solving this equation, we are cutting something in half every time. This is often the most classic example of this is called a binary search. That is something we'll learn later this week. And the way I want you to think of binary search is we have something that's completely sorted. Like, let's pretend we have a phone book that's sorted by names, right? So we have Adam at the top and Alexis lower, all the way down to Zaworski, right? And so if I said to you, hey, could you look up me in the phone book? Look up Corey. Would you start on page 1 and flip through it from one thing to the next thing to the next? No, right? But if you did, that would be a linear search, because you would be looking all the way through the phone book until you find my name. But if you were a little bit more clever about it, you could do a binary search where we could say, okay, I'm going to open the dictionary in the middle, the phone book in the middle, and I'm going to look at where I'm at. So I open it and I'm at M, right? And I go, okay, well, is Corey before or after M? And you go, well, Corey's before M, right? Because C is before M. So I'm going to take the first half of that phone book, and then I'm going to open that in half, split that in half, and I'm going to look at where I'm at. I'm going to go, okay, now I'm at F. And I go, is F before or after C? And I go, okay, well, that's after C. So I'm going to go to before where I am. So I'm going to take the first half of that. I'm going to split that in the middle, and I open. I go, okay, now I'm at C. And then, you find me, right? So so instead of going all the way through that every letter at a time, we're jumping and halving it until we actually come to our solution. And that is a logarithmic solution. So if you remember from math days, a logarithmic graph looks like this. And it eventually starts to flatten out, although it never actually flattens out. That's like its asymptote or something. And every time, and the base of a logarithm is like the answer from the base is if you divide by that base, how many times it would take to like reach 1 or 0. I don't 100% remember anymore. It doesn't really make sense, matter. All you have to remember is if you're cutting the same thing every single time by a certain portion, like in half, that's logarithmic or log n. Okay? Let's go back. Let's keep moving. So we have our constant, then we have our logarithmic, then we have our linear. What's next? Let's write in the chat what comes next on the count of 5, 4, 3, 2, 1. What do we got? All right. So Deja, I'm saying you say linear. We just did linear, so it can't come next. Doug says quad. Jay Jones says quad. Henry says quad. I think Henry changed his, though. Didn't you have something else? Henry before had n log n, but he changed it. David said n quadratic. Kevin said saying linear. We just did linear, so it can't be that. Marvin saying quadratic. Kong. People have switched their answers. So, okay. I'm seeing some people started at n log n and have switched. So what does that mean? Okay, excellent. Yeah, Deja, Javon, I like that. The next thing is actually O of n, and you can think of this as a times log n. This is called linear arithmetic. Rhythmic. Okay, so a linear arithmetic algorithm is kind of interesting. And what you really want to think of whenever you think of linear arithmetic is sorting. Okay, specifically merge sort and quick sort. And any of the like built-in sorts. You can write slower sorts. But for the most part, it's the ones that are built in, and the merge sort and quick sort, those are n log n, linear arithmetic. So let's talk about that. So if I'm sorting something, let's like look, I'm gonna need the internet for this, I think. Let's see a visualization of merge sort. So if we look at an image of merge sort, it's going to look something like this. how do I just, okay, well, it's going to look something like this. So remember an image like this because you might need to remember that someday. But so if we want to sort stuff, we have to still go through every element, right? Because we can't just, without looking at the element, we can't magically put it in its right place, right? So we know it has to be at least n because we have to observe every element. Now, where does the log n part come from? Well, we could sort it in this kind of way where we continually split the array in half, making these smaller and smaller arrays as we go. So if we're, and we will go more into sorting on a different day, but like if we're looking at this array and we see 38, 27, 43, 3, 9, whatever, we could split this in half and we could say, okay, we're going to sort this first half and then we're going to sort this half and then we can just merge them together because merging them is just going to be an n. Like we read across, we can merge two sorted arrays. We'll see that at some point. But we go, okay, well, look at this level. This is a recursive function, by the way. And we go, okay, well, I could split these up more. So we split these up more. So now we just have these really small arrays to sort. And then we split these up even more. So now we have all of these arrays of individual that are just by themselves. And the step when we're bubbling back up the recursive stack is merging these two sorted arrays. So we can go, okay, 27 goes first, then 38. And over here we go 3, then 43. I'm just gonna stick to the side because it's the same thing for the other side. And then here we merge these two and we go, okay, well 3 goes in, then 27, then 38, then 43. So we're still touching every element. And then finally, we merge these two sorted arrays, right? All of these are already sorted, but that's because we kept breaking these down in half at a time to make a smaller and smaller arrays to make it easier and easier to sort. And so in doing that, we end up getting n log n. Okay? Let's keep going. On the count of 5, I want you to tell me the next slowest one. Okay? 5, 4, 3, 2, 1, go. Ooh, okay. Crystal, I see you. Karen, Marvin, Siham, Sin, Gavin Wong, Rafid. Nice. Kong, Melbourne, Shia. Excellent. Excellent, excellent. This time we're getting, again, a unanimous quadratic, but this time we are correct, right? So our next one we want to look at is n squared. This is called quadratic. Who can tell me when we're going to see quadratic functions? I know I'm spelling things wrong. Oh, I see people in the chat. Cool. Yes. Excellent. Thank you. Ashia, David, Deja, Nelbur, Marvin, Javon, right? This is when we are thinking of a nested loop. So for every loop nested, increase the exponent by 1, typically. So if we have a for loop inside of a for loop, and they're iterating through the same iterable, like a string or an array, then that's quadratic. And I will show you why. Okay, so let's stop the share. Let me grab my whiteboard here. My nifty whiteboard. I see. I have to turn off the virtual background. Un momento, por favor, as they say in certain parts of America and Mexico and anywhere that speaks Spanish. Okay, and we will say, lost my train of thought. Help me. What was I demonstrating?
Quadratic.
Quadratics.
And nested loops, I think.
Thank you. Okay, so let's say we have an array where we have, let's say, 1, 2, and 3, right? So we just have 3 elements in this array. And we've got 2, 2 loops. Now, Henry, in Oregon, they say, uno momento por favor. Okay, and so I've got this for loop, and let's say I'm doing let I equal to 0, yada, 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 right? And I have my for let j equal to 0, yada, yada, yada. And I'm iterating through it, and we can look. So let's say we wanted to take like a slicing or something of how the array moves, and we could say, okay, well, I, or whatever, we'll just look at where each I and j is. So we say I is here, so I points to 1, j points to 1. Now j gets incremented, so now I points to 1, j points to 2. I points to 1, j points to 3. Gets to the end, I gets incremented, and j starts back down at 0. So now I points to 2, j points to 1. I points to 2, j points to 2, I points to 2, j points to 3, right? So we have this, and then j's loop ends, and we'll go back up. I gets incremented in our top loop, so now I points to 3, j points to 1, I points to 3, j points to 2, I points to 3, j points to 3. So what's that mean? Well, we touched the elements 1, 2, 3, 4, 5, 6, 7, 8, 9 times. There's 3 elements in there. 3 squared is 9. That's quadratic, right? Now, sometimes people might say like j is equal to I plus 1. So we'd have a few less. We'd have I is 1 and 3, 2 is 2 and 3, and then 3 would just be 3, let's say, and that's better, but it's still considered quadratic as things approach infinity. There is a proof for all that. I don't want to do it. I just want us to understand this part. Okay, so a nested loop gives you quadratic. Okay. All right, let's keep rolling. Let me turn off this heater. I'm dying. All right, great. Okay, so let's keep rolling here. Okay. The next speed. Put it in the chat in 5, 4, 3, 2, and 1. What do we got here? Let's see here. Seeing exponential for the most part. Henry, I see you say n cubed. Interesting. Ashia says expo. Okay, good. So we got some good answers here. We are going to say that we're going to go to O of n of 2 to the n. Whoops. N this time. Whoops. And this is, in fact, exponential. So, Henry, You are right that n cubed is slower than quadratic. But then we would say n to the fourth and n to the fifth and n to the sixth. So that's an important thing to note and to be able to recognize what it really is, because maybe it is n cubed and whatnot. That is important. It doesn't have to be quadratic. It could be n cubed. But since we could do that for everything, like in the typical charts we'll see, let's see if I can, where is my, I have some chart somewhere here. Hang on. This chart. You typically don't see anything more. Like, I don't want us to see the answers coming up, but we see this bottom line here is O of 1, constant. Then we see our log n, our n log n, our quadratic. But then we see our 2 to the n, our exponential. And so everything in here you can think of as n to the whatever, but then everything past here is 2 to the n. Okay, so let's keep. So examples of 2 to the n. What's a common, what's the classic case for that one? Who can tell me?
Fabio Canse something?
Sorry, Siham?
Is Fabio Canse they call it? I don't know.
Oh, I see. Okay.
What's your
Yeah, that's right. So the pronunciations are soft, but you're totally right. It's Fibonacci.
Fibonacci?
Perfect, right? So Fibonacci, specifically the recursive Fibonacci that does not make use of something called memoization, is exponential. So let's say Fibonacci I don't know how to spell it, solved without memoization and recursively. So let's see why. So let's go to Fibonacci. So Fibonacci is another classic problem that deals with recursion. Let's see if they're going to give us. Okay, you can see this tree, hopefully. And the Fibonacci of 5 is the same answer as the Fib 4 plus the Fib 3. And the answer for Fib 4 is the same as our Fib 3 plus our Fib 2. And Fib 3 is Fib 2 plus Fib 1. Fib 2 is Fib 1 plus Fib 0. And so with every single call, with every single recursive layer, we have to make 2 recursive calls. And the tree just keeps expanding, right? So if we had just Fib 1 and Fib 0 are constant. They're like set. We don't have to worry. But when we go to 2, for one thing, we have to make 2 calls. Now, for the next one, we have to make 4 calls here. And then we see if we have Fib 4, all of a sudden we're making 5, we're making 8 calls. And then when we're just at Fib 5, now we're making 9 and 10, 11, 12, 13. Now we're making 14 calls. So this kind of growth becomes huge. And if we actually solved Fibonacci this way, by the time you looked for the Fibonacci of just like 100, you'd be sitting by your computer for quite a while because it has to make so many calls. Now there is better ways to write this, which we'll learn at some other point in time. but this is the classic example of a exponential big O time. Okay. Okay, let's hit the last one here. In the chat, go ahead and tell me the next slowest one in 5, 4, 3, 2, 1. Rock and roll. Okay, Phil, fast on the keys. Deja, thank you. Henry, Giovanni, Marvin, Javon, Nilber. Cool. Bujwagabasi, Rafid, Wong, excellent. Okay, and right, I'm getting a lot of factorials, and that is correct. So factorial is n exclamation point. In math, that means factorial, and that is factorial. And so the way a factorial works is it is the answer for 5 factorial is 5 times 4 times 3 times 2 times 1. That's just like what math is. But the classic example for this, does anybody know?
It isn't it just finding the oh, you already voted. Okay, never mind. I had the thing blocking it.
No problem. Okay, so the classic example of something that takes factorial time is permutations. So permutations are like if I had an array of 1, 2, 3, I would have to give back an array of 1, 2, 3, 2, or I say 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 3, 2, 1, and 3, 1, 2. I think that's going to be, put that on its own line. Right, 1, 2, 3, 4, 5, 6. Is there other orders that I'm forgetting? I don't think so. But with permutations, this number grows very, very fast. So when we have 3, we're giving back 6. But if I add a 4, all of a sudden there's just so many more options that we can make. And so to build out all of these permutations takes quite a while. And your app can start to get really slow. I don't think there's a really good, efficient way to write permutations, unfortunately. But that is the classic factorial example. So if you ever ask a problem where you have to write permutations in an interview, and they ask you how long it takes, you would say permutations, or you would say factorial, sorry. You wouldn't say permutations, because then they would say, right, that's the name of the problem. What's the time complexity? So it's a combination of all the ways you can write the array. Well, right, it's not, thanks, Fowler, not just anything. Arrays, it's anything. This is just a classic example of permutations. Okay, so this is our big O.
Hey, Corey.
Yes.
Can we just clarify the example for logarithmic? Like you said, we look at we look at the split of the object that's closest to the element that we're looking for, and then we repeat that action, right?
Yes, so it's the idea of splitting our data or the thing that we're working with in halves each time. So we're dealing with smaller and smaller halves with each iteration, because things cut down very quickly when you're doing that.
So would that be say if object at key of I equals to such and such, like that, to kind of analyze the two splits.
I think you broke up for part of that, so I didn't really hear you. I'm sorry.
Oh, like how do we analyze the two splits?
If you are taking n into your argument and you are splitting that in half each time and dealing with half of it, then you are probably writing a logarithmic function.
Okay, gotcha.
So if you had an array of like 10 things, you would simply like use like split and split at index 4, and then would look at the last element, and so you could see, so you look at the last element in the first one and then the first element, because you're looking for what you want.
So log n is going to split it for me, or do I have to split first and
no,
then
log n is the time complexity. You have to still write the whole algorithm.
Okay, that's what was confused.
It's
okay,
not a method. Yeah.
Okay.
Yeah. Okay, so let's keep, we're all in here. So this is your big O complexity chart. Memorize that. That's something you should know. Okay, let's derive some runtimes. So this function here, I want you to look at it, take a minute, and then in the chat, on the count of 10, I want you to tell me the time complexity of this function. In 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. What do we got? Okay, Karen, Maria, Deja, Phil, Henry, Kong, Sam, Rafi, Giovanni, Marvin, Danny, Kevin, David, Siham, Crystal, Jay, and okay, and Ashia. This, most everyone is correct. This is going to be linear. So the reason for that is because string, we are iterating through something of unknown length. So we don't know how long our string is going to be ahead of time. So we are going to look at each thing and we will be iterating through the whole array. So that will be linear. Right. Now Jay puts up an interesting point. Jay says constant best case. Yeah, kind of. So there are these things called best. You can think of things as best case, average case, worst case. It's also called omega, o theta, and o delta. That's right. Those are like the three different types of big O. And they all look at different types of things. They do look at from best case, worst case, and average case. But typically when people are talking about big O, what we really care about is the worst case. So yes, the very first element in our string could be the target character, and we could just return right away out of it, and that would be awesome. And we're only going to go all the way through it if the target character isn't in there, because we're going to be stopping. So if the character is in the middle, we're only iterating through the middle. But by and large, we don't usually care about any of that. I mean, it's good to know that there's that it's not always going to run at the same time, even if given the same size of n, right? There are best cases, worst cases, average cases, which are like theta, delta, and omegas. But we're really just caring about the worst case, average to worst case n. For an example like this, we would say linear O of n. Okay, let's try another one. Okay. How about this problem here? What's this one? In 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Show me the money. What do we got here? Okay, I'm getting a lot of constants. Awesome, right? You didn't fall for it. Just because there's a loop doesn't mean it's linear, right? That's when we're iterating through n. But here we're not iterating through this array. We are iterating from 0 to 1,000. So we're always doing 1,000 loops, or what? What? I know it's not 1,000. I'm sorry. I don't know what number that is. It's gonna be 1,000 by the time I'm done with it. All right, Rafid. Thank you. Rafid, the guy that works at the bank, he knows like that. Henry too. Yeah, right. Because of the 1,000. All right. Yeah. I know. I can't read. I can't spell. It's okay. But we're at 1,000 loops every time, no matter what the size of the array is. We don't care. It's because of that. This is constant. Excellent. Thank you, Henry. I still love all of you as well. Okay, let's keep rolling. Let's look at this one here. Let's bang this out. Example 3. What is the time complexity of this? So look at that. And we see 10, 9, 8, 7, 6, 5. Do we know what contains is? Oh, yeah, here it is. I didn't get the whole thing. That makes a big difference. 5, 10. Well, let's look at it again now that we know what's going on. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. What do we got? I'm getting lots of quads. Danny, Kong, Rafi, Giovanni, Doug, Karen, Kevin. I'm sorry if I missed some of you. The chat moved fast. Sin. Okay, great. So I did see a linear in there. So there is some tricks here, right? So contains function. Well, we've already seen contains essentially right here. It was called example 1. And we decided that this one was linear, right? Because given the size of the array, we don't know, but we're going to iterate through the entire array. But our example 3 here, if we just look at it like this, we go, well, this is also looks linear because of this loop. But if we look a little bit closer, inside of this loop, we've got this contains. And contains is also linear of the same array. So if we have a loop where we're going through the array, and within each loop, we have another loop of the array, we do end up with quadratic. O of n squared. Great. Okay. Let's see what's an interesting one. Don't care about these. this is fun. Okay. I like this problem. So I want you to look at this problem and tell me what the runtime is. Right? So think about it. Take a little bit of time here. Don't write it yet. Don't want to give it away. Don't want to just give away the big O. We want to earn it. Okay. All right. On the count of 10, right? 10, 9, thank you, Doug. 8, 7, 6, 5, 4, 3, 2, 1. What's going on? Oh, this is great. We got no clue as a class. Thank you, Giovanni, Phil, Jay, Marvin, Danny, Karen, Siham, Deja, Kong, Maria, Rafid, David, Henry, Marvin. Marvin wants to use a lifeline. Kevin and Doug. Nilber's sliding into the DMs. Sin, you combine some. Interesting. Okay, so let's talk about it. This part here, we know is constant, right? We've already seen this one. And this one here, and that's constant because it always is 1,000. This time the number really is 1,000. Pretty sure. And this line here, right, we're iterating through an array of unknown length. So we know that this is O of n, right? No. But then here, we have a nested for loop where each one is iterating through the array. So this stuff is n squared, right? We know that. We've seen that quadratic. This line here is constant, so we don't really have to worry about this. Constant for comparisons. Making a
the square.
Oh, thank you. Crucial. Yeah. So we see we've got these 3 different time complexities in here. And so you could say that it's like, O of, gosh darn it. Sorry. You could say it's O of n squared plus O of n plus O of 1. You may be tempted to say something like that. And you're not wrong. That said, as n approaches infinity, so let's say n is 1, right? And we say 1 squared. Okay, that's 1. This is 1. This is 1. That's 3, we'll say, right? We go, okay, that's fine. But then let's say n is 5. If n was 5, we would say, okay, well, that's 25 now. This is just 5, and this is just 1. Now let's say n is 10, right? So if n was 10, all of a sudden n squared, so that would be 100. This would be 10. This would be 1. Now, what if n was 1,000? 1,000 times 1,000 is something very big, right? 1, 2, 3, 4, 5, 6, maybe. I think it's maybe 1 million. And we would still have 1,000 here. And then we would have 1. And as you can see, as n starts to approach infinity, there's only one of these that really has any weight. There's only one that matters. And that's this one. Because this number is growing so much faster than everything else that we don't really care about these. as n approaches infinity. And so what this really comes down to is O of n squared. That's all we really care about.
So Corey,
Yes.
so the other, like the ON and the O1, those two, they're, I guess, like they're so small in term compared to quadratic that we don't even, like, we can ignore it.
That's correct. They're so small that we can ignore it. Because when we're thinking of the speed of a function, we want to calculate it by its worst time complexity.
Okay.
Because if I say, well, okay, so the first part of this function is going to take an hour, and the rest of it's going to take it's going to take 30 seconds. So we have an hour and 30 seconds. You would say, okay, I don't really care. It's an hour. You know what I mean?
Yeah.
Right. So if I said, like, okay, this program's a year. Today's one class. We're going to take an hour going over this. You know, you go like, yeah, whatever. Like, it's a year. The program is a year. Right? Because that's really the whole amount of time. So you take the largest one. Okay. Now, let's see if the next example is one that I like. Not yet. Okay, I'm going to write one. So let's say we have a function. Function, I'll say, what's this? Whatever. I don't care what that is. This takes in an array. And I will do for let element of array log my element. And then here, let element of array log my element. Okay, good. So, okay, in 10 seconds, I want you to tell me what the time complexity is of this one. That's in 10, 9, 8, 7, 6, 5. You guys are so fast. 4, 3, 2, 1. Okay, now everybody else post your answer. Thank you. Okay, Crystal, Sam, Deja, Giovanni, Phil, Karen, David. Everyone else was early, I think. But I see you, and I appreciate the entering. I appreciate the excitement. Yeah, this is n, right? Which is interesting because we have an n here, and we have an n time thing here. And so you could easily think of it as like, oh, this is O of, I hate when that does that. It's like a pet peeve, I guess. Oh, mother. And you could think of it as O of 2n, right? Because we're iterating through this 2 times. However, and this is correct, this is true, but as n approaches infinity, the 2 matters less. We don't have to think about that. And so when we're dealing with big O's, we actually remove the constants with numbers. So when dealing with big O, remove the constants when calculating. So because it's always 2n, we can just go ahead and get rid of it, the 2. Okay, let's do 2.
Wow.
Let's do 2 more examples, I think, is all I care about. Maybe 3. Okay, this one here. The do stuff. I like this. Do stuff. Henry? Think about this one. There we go. Okay, on the counts of five. 5, 4, 3, 2, 1. What do we got? Yeah. Oh, yeah. Seeing some interesting things here. Seeing some cubes. Seeing some exponents. Okay, what do we got? What do we got? What do we got? Not constant, Doug. Okay, so I've seen a mix. This is cool. So there was a little line here where it said, for every loop nested, increase the exponent by 1. So let's look at that. So if we're iterating through our array, we have this is n, you could think of to the 1. This, we're inside of this, so we have for each iteration, we're doing another iteration. So this is going to be our n squared. Now, if the function ended here, we're in quadratic. However, now we're doing another loop for each one. So we're going to increment the exponent by 1 here, and we get our n cubed. This is a constant thing, so I'm just going to ignore it because it's smaller than what I'm already dealing with. And this is our answer. So this one is O of n to the 3rd, or cubed. Okay. Any questions on this one? So, just as mentioned prior, because there's just kind of infinite number of exponents here that we could have. So that means quad. You would actually say n to the 3rd. You probably wouldn't say the word quadratic, I don't think, or you would say n cubed. So these are the way you can typically break these down, but since quadratic is like for 2, which is just the next start, and typically what you see, anything else, you would just kind of say n to the, and you would say how deep in you are, essentially. So it's closer to quadratic than it is to exponential, but it's actually n to the cubed. Okay. Let's do another one. This one I really want you to remember. Okay. I want you to, don't write in the chat yet. I want you to take a minute here and look at this one and seal this one into your brain as well. So I just want to also mention that there is like a DSA exam at sometime in May after we've reviewed all of the material for DSA stuff. So, well, or at least the material that will be on the exam. So I cannot tell you exactly what will be on the exam, but there are things that I say that make things obvious. And if you pay attention to those things, it should make life easier. So anyway, that's just a little preamble. I would remember this one. And let's write what we think it is in 10, 9, 8, 7, 6, 5. I want you to actually, hang on, before we get in, I want you to tell me which each one of these is. Tell me what foo is, and then tell me what bar is. All right. In 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Blast off. What do we got here? What do we got? 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 Getting some good action here. That's what she said. Crystal, Karen, Siham, Marvin, Phil. Excellent, Kevin. We got Denry. David. Okay. K. All right. Ashia, Doug, Henry. Nice. Okay. Let's dissect this one. First thing, let's look at foo here. So foo, we are iterating through this array. We don't know the length of this array ahead of time. So we don't know how many iterations. So as our array gets longer, our number of iterations increases. And therefore, this one here is O of n. Awesome. Awesome possum. Awesome possum soup. And then we have our next one, bar. Okay, and let's start dissecting this. So the first thing we do in bar is we call foo on the array. Well, we know that's O of n. We've already seen that. We know that. So this line is O of n. We go, okay, cool. Whatever. That's our current max. Then we have a for loop. And we see, okay, our for loop is iterating through our array. So we go, okay, that's O of n. All right, this for loop is O of n. But what's in the for loop? So we see, oh, inside of the for loop is our O of n again. So if this is inside of this, then it's O of n squared. Well, like that. Okay, so good job. Pretty much everybody nailed that one. So that's awesome. Just gonna do this one as well, because this is important to know in life. All right, so in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hit me with your best shot. Okay, so we've got seen a few things here. Danny, is that I don't know or I don't care with the K? Okay, we are seeing things. Henry, you can't just say what Doug said. That is not gonna fly. Marvin says log. David says n log. Ashia says linear arithmetic. Giovanni says linear arithmetic. Phil, linear arithmetic. Maria, Lynn Rith. I like that. It's short and cool. Kong says exponential. Danny says IDK. I love Donkey Kong. Rafit says linear arithmetic. Karen says linear arithmetic. Deja says quadratic. Henry says n log n. Linear arithmetic log. I'm seeing a few mixes. So the answer to this is we have a sort. So this here is just a constant operation, right? This is just checking to see the length of something. So this is going to be O of 1. Our first line. But this line is where stuff happens. So a sort. It's a built-in sort. What is a built-in sort? Sorting, merge sort, quick sort. Any built-in sorts is n log n, aka linear arithmetic solution. Okay, so this isn't log n. I saw some people put in log n. Log, it would be impossible for us to sort something by only cutting it in half. We sort things by cutting it in half and comparing every single element. So by doing those two things, it's n log n. We need both. Lynn Rith, Danny. Yeah, cool way of saying that. Okay, so that is our big O practice. I think that's good for the morning.
Could you please repeat the last example?
The sort is n log n.
And log n. Okay, thank you.
Yeah, no problem. So that's because we are cutting that array in half to make smaller arrays, but then we still have to iterate through every element. to touch and compare the arrays so that we get all the elements back. So we have to touch them all. So it's at least linear, but since we split it up as that technique, it's n log n. Okay, so that is your big O review. Remember all of those things today, please. And we will still talk about the time complexity of things as we write functions. Please make sure that I do that. Please remind me if we write a function on a DSA thing, ask, what is the time complexity? Be curious about time complexities. Space complexity is also a thing that we should probably mention. It's not usually as big of a deal, but I'll tell you. Actually, I'll write it in the form. I'll just write it down too, so you have a way of referring to it. But let's just talk about space complexity real quick. Space complexity is still something that's asked. So space complexity usually deals with similar things as these. I'm going to say the most common ones that I've seen is O of 1. So this is when no matter what the size of your input, like you're only using same number of variables. So like no same number of variables no matter what. Space complexity can get a little bit more complicated with recursive functions, because every time you make a recursive call, it's a function call that gets added to the call stack. It creates a new stack frame, so that technically uses up some more memory. But that gets a little bit more complicated. I don't really want to go into that right now. Same number of variables no matter what. Let's say O of n, which would be like creating an output of equal length in relation to the input. And this is kind of like usually what you're dealing with. All right, so I'm just gonna like leave that. So this is constant memory here. We're just returning true or false. There's no variables. There's nothing for us to think about. This one has a variable, but it's always just this one variable. So this is, again, constant space. We already saw this one. This one here doesn't use any extra space. So this sorting could use extra space because it uses stack frames and recursive calls, depending on how that sort is implemented. Otherwise, this could be using constant space because this actually mutates the array. But let's say I had a function like this where I said like function my map that took in an array and a callback. And for each element, let I equal to 0, or I'll just, okay, let's say I have an output. I'm building the map function, right? And I say for let element of array, and I say output.push callback of our element, return output. In the chat, I want you to tell me the space complexity of this. Okay, complexity. Go ahead and do that in 5, 4, 3, 2, 1. What is the space complexity on this? Okay, we're slowly writing answers here. Yep. Thank you, Deja. Kevin, Maria, Danny, Marvin, Karen, Sam, Nilber, Henry, right? This is the space complexity is O of n. This is linear because for every element in this array, I have to add a new element in this array of equal length. So this output size is going to grow in comparison to my array's size. And so because of that, our space complexity for a problem like this is O of n. Okay, so space complexity works pretty similar to time complexity, and that's also something that we should talk about as we continue to learn different data structures and solve problems. We can talk about time and space. Time seems to get the bigger emphasis now, especially because space seems kind of cheap. There's a lot of room for space. Okay, any questions about anything? All right, let's meet up again after lunch and we'll do a small review on recursion. But until then, work on whatever you need to work on, and we'll be around to answer questions if you have any, okay?